Okay, so the electricity magnetism stuff that we did or started yesterday is kind of crazy cool, but it's also just weird. So we'll go through, take a look at a few different slides here to try to clean up what we tried to start yesterday. Hope this helps. So magnetic fields, the symbol for a magnetic field is uppercase B. It is a vector. It has a size and a direction. Magnetic fields interact with other magnetic fields, and they also interact with moving charges. So magnetic fields don't interact with everything. They interact with some specific things. Just like gravitational fields only interact with other masses that produce gravitational fields, or electric fields only interact with other electric fields produced by charges. Magnetic fields only interact with other magnetic fields or moving charges that also create magnetic fields. There are two things that are useful to talk about when we talk about magnetic fields and moving charges. Well, there are a number of things, but what we'll look at right here, one of them is the size of the force. So when a magnetic field is present and a moving charge exists in that area, the magnetic field produces a force, or there is a force produced when a magnetic field interacts with a moving charge. So it's convenient and useful to be able to talk about how big that force is, the size of that force. That's number one there. And then number two, the direction of the force when that magnetic field interacts with the moving charge. Normally, when we've been going through and doing things, we've been focusing on calculations. We're trying to get some other things figured out, but the calculation part has always been a significant part of our work. Today, when we go through this stuff, we're going to look at it and try to get a feeling for the calculation, but that's really not an emphasis. So here, the size of the force when a magnetic field interacts with a moving charge, it depends on the amount of charge, how fast the charge is moving, and the strength of the magnetic field. So the force is the charge times the velocity times the magnetic field. Now, when I say times the magnetic field, really you see that there's this weird X there, and up here I said it's crossed with. Those things, it's a little bit different. So this actually ends up being an advanced mathematical thing when we talk about crossed with versus multiply. They're actually kind of different. We won't go into the weird differences between them. In terms of a mathematical operation, that's when we're going to start doing our right-hand rule stuff in a little bit. So the direction of the force that a magnetic field exerts on or interacts with a moving charge. Force, velocity, and magnetic fields are all vectors. That means that they all have a size or a numerical value, and they all have a direction. Now, nobody knows why, but for these things to exist, for a force to be exerted on that moving charge, the magnetic field and the velocity must be perpendicular to each other. And when that happens, the force is perpendicular to that as well. So we have three things that are perpendicular to each other. So this is the first time in a physics class where we're trying to look at these things, where we've had to look at not just up and down or left and right, and not just both of those, bloop, but we also now need to add a third direction. So I've got my thumb going up and down, my pointer finger going in and out, and then my middle finger going lefty righty. So the three dimensions there are a different sort of a deal. But it's just the way the world works. It's the way the universe works. In physics and in science, we try to figure out more and more details about the rules of the universe, but we can't really say why the universe follows those rules. It's just the rules. So we'll do a little bit of practice on some of these things in a minute, I guess. Forgot about this slide. So the right-hand rule stuff, we'll go with this version instead of this version. So with this version with your hands, your fingers point in the direction of the magnetic field. Your thumb points in the direction the charge, a positive charge, moves. And then normally, like when you push and pull stuff, you do that with your palm, the palm of your hand. So the palm is the direction of the force or the direction of the push. Thumb velocity, fingers magnetic field, palm is the direction of the force. And this is one of those things, again, where it seems weird, but it's the rules the universe follows. And so we try to, as physicists and scientists, folks try to find a way to apply these things in a way that's usable and predict and can be used to predict things for other calculations. So here's an example. We've got a charge moving to the right. So the charge is going that way. We've got a magnetic field going up. And then if we're going to try to figure out the direction of the force on that charge, we need to go through and use our right-hand rule. So the positive charge is going to the right. The magnetic field is going up. And now we'll use our hand, our right hand. Has to be your right hand. It doesn't work with your left. Things get all buggered up. So we use our right hand to figure out these directions. So now my fingers point in the direction of the magnetic field. The magnetic field is to the top of the screen, so I go like that. And then my thumb points in the direction the positive charge is moving, and that's to the right, so like that. And now my palm, just by the way I've got my hands and thumb, my fingers and thumb lined up, the palm is in the direction of the force that would be exerted on the charge. So with the magnetic field up, like the North Pole pointing up, the velocity of the charge being to the right, the force on the charge would be into the screen. Which means that as the charge goes this way, it would be going this way, it would experience that force and it would be kind of curving in. So it would be going like this and it would be experiencing the force curving into the screen, experiencing that force. So this next page shows us that slide, that act going on. So if you don't like my talking, there's an image to show you what we've got. Another example. And we do another example because there are some weird things or some subtleties that we need to be prepared for. Now when we go through and do these things, your fingers always point in the direction of the magnetic field. Your thumb always points in the direction of the velocity of charge. Your palm always points in the direction of push. But it's not always going to be like this. You might need to turn your hand. You might need to rotate this way or this way or this way. So that's a part of the thing we need to practice. So for this problem, our fingers should point with the direction of the magnetic field. And I really suggest you have to do this along with it. If you just try to look and think about it, it's going to be tough. Physicists at all levels, when it comes to these problems, take their right hand out and they start doing this stuff. High school kids, college kids, physicists that are practicing this stuff to try, that know this stuff but are using this stuff in their practice as a professional. When they're doing this, take out your right hand and there you go. That's just the way it is. So don't do this without taking out your right hand. Take out your right hand. Move it around in the right directions. So magnetic north on this points up, so fingers up. The charge is moving to the left, so I stick my thumb out, but this is going the wrong direction, so I need to turn it like this. So magnetic north is up, the charge is going to the left, and then that means that the force is the direction my palm would push out of the screen, away from the screen. Thumb this way, magnetic field that way, the force this way. So when we have it like this, the charge is moving this way, the magnetic field is up, charge this way, force this way. So the force this way means that as this charge moves, there's a force pushing it this way, and it would come out of the screen. Another image, just to show you that if you prefer a diagram as opposed to a person. So this one, again, another example with things arranged slightly differently so you can see how things are lining up. This one says that that positive charge is coming out of the screen, so that means my thumb must go out of the screen. Yeah. So now my thumb is going out of the screen. The magnetic field, magnetic north, is up. So I'm looking at something like that. And now it's the force on that charge is the direction my palm faces. So the force would be that way. So the charge is going out of the screen. Magnetic north is up, and the force is that way. So that means that as the charge is moving, it would go like this. So as the charge is moving, the force on it would be pushing it that way. It would end up kind of going. And there's a diagram for you again. I think I've got one or maybe two more, I think. So, oh no, I think this is the last one. So for this one, now we have, there's kind of weird drawing diagrams for this. So for this one, I have the magnetic field coming out of the page. So when I do this stuff, magnetic field out of the page, that way. And then the velocity of the charge should be the direction my thumb is pointing. So I need to take my hand and rotate it. Yeah. So I've got, trying to make it so it's in screen here. So I've got the magnetic field out of the screen. My thumb is going in the direction of the velocity of the charge. Then the force would be up. So magnetic field out of the page. The velocity of the charge is the direction of my thumb. The force would be up. So that means that as the charge is going this way, it would experience a force up. So the charge would go curving up. I hope that helps a little bit. What we really have to do is just kind of keep thinking about which direction your thumb, your fingers point, and you have to kind of rotate and take your palm and move things around in weird spots. So I'm going to add a couple of questions. The only thing that we're really going to be focusing on is the direction of things, finding the calculation, a charge times the velocity times the magnetic field. It's, you know, multiply, you're done. I'm not concerned about your ability to do that. You can do that. The thing that I think is much more interesting is the way the universe works, where everything is at these right angles to each other. That's really, I think, really unusual, and I think that makes it really cool. So that's the end of this video. Like I said, there will be a couple more questions for you on these lines for work to do today. 13 minutes is a bit long. Sorry, guys. Good luck.